எனக்கு இப்படியா சரி பி பற்றி கிடைக்கும் எனக்கு இப்படி படிக்காச்சு Did you both come together actually? Something like that. Because அது சொல்லி சும்மா மூணு நேரம் மூடி கொஞ்ச நேரம் இவங்க லவ் பண்ணுறது கேட்கறது விட நீங்கள் தான் கேட்குறது நீங்கள் வெளியே வந்தாலே வந்து கீழே வந்துட்டாங்க
In the first workshop, so we used a couple of supervised unsupervised techniques. So the first one was PCA, right? Then the next was CSME, right? CSME, and we also used hierarchical clustering. Okay. So these were the three unsupervised techniques that we used. And so now the thing with these are biased methods, right? So these are biased methods. It depends on the viewer to find out the number of groups, right? So we went for an unbiased method, that was NMF. So that was the method that we used to get out the real number of groups.
Is NMF also unsupervised?
It's also unsupervised. So when we used NMF, what were the plots that we used to determine the number of groups? So three types of plots we took out from the NMF results, right? So one was the consensus plots, right? The other was the coefficient maps, and the third was the NMF survey scores, right?
Can you repeat all three?
Yeah. So from NMF we got the consensus plots, right? The coefficient maps, and the NMF survey scores. And also we used the silhouette the bar graph to get the groups, right? The silhouette plots, right? So first you need to first now in your assessment you need to describe the data what you are going to use. Okay, so it's mentioned in the beginning of this report. It's the family data set, right? So I think the paper for this is provided for you. So you can mention how many genes you took for this experiment, right? You can also get it from here using the team expression. Okay. So how many samples and how many genes are given here, right? That's the initial data set. So how do you get the number of samples? You take a look at
Rows. G, C.
Yeah. So you have to take a look at the data set. You can see it's the columns, right? So this GSM, those
All of
are
the
the
samples.
samples. Okay. So these are the probes. So this is a microarray data set. Okay. Measuring gene expression from medulloblastom patients. So those are the probes. And you have the expression values. Okay, so the first technique we tried was PCA. There are two things you need to keep in mind at this moment. Okay, so you have this table, and then you have this plot, right? So you need to be able to extract information from both these. Now from the table, what you need is this cumulative proportion, right? So that's that describes how much of variance is described by each principal component, okay? And this cumulative represents the addition of the variation, right? addition of the inscription. Now, when it comes to PC3, okay, so you can see that's 0.42. When you convert it as a percentage, that's around 43%. Right? 42.9, that's not
Means
40.
that means altogether 1, 2, 3 altogether 40.
Yeah, yeah. All
Not just
together,
one.
no.
Not just 3.
Not just three. All together, those three, the first three principal components describe around 43% of the variation of the data set. Okay. So, so those are the three that we are going to have to use. So how do we use them? We either can use a 3D plot to plot all three principal components together, or we take two of them at a time and plot them, right? So when we plot PC1 and PC2, okay, now you will see that certain groups, certain samples, so each dot represents a sample. Some samples are clustered together, they are close together, some are far apart, right? So close together means they are more biologically related to each other, right? So based on the clustering patterns, you can identify the number of groups. So how many groups can you see here?
3.
3, right? So that's around 3. So some people can say it's 4. So once again, as this is biased, it depends on the user, right? But in your report, you have to mention how many groups you roughly saw. So use these questions as guideline, right?
Means if we are showing the 2D plot, are we supposed to give both the plots like PC versus PC1 versus 2 and 2 versus 3 like that?
One is enough.
One is
So
enough.
if you look at both plots, I think PC1 and PC2 give a like better separation, right?
Or else instead we can go with 3D plot, right?
Yeah.
If not.
You can,
Okay.
Okay. Now next, you have to get the TSNE plots, right? So now, when it comes to TSNE, you have to mention, you have to now for each technique, you have to provide a bit of description, right? So we did PCA, that's not enough. You have to describe what PCA is, right? So give a brief introduction and then describe the results. So the same for TSNE. Now you have to mention about this perplexity as well, right? So what is perplexity? And its effect, right? So depending on the values of the perplexity that we input, the number of groups that we get also differs, right? So we have to select the best perplexity for our data set. Okay. Now, how many groups can you see here once again? It's around 3 to 4 groups, right? So I mentioned that again.
Yes, what will the perplexity finally be optimized for? 30 or 20?
13, right?
We did with 10, 20, 30.
So you can mention that. So that's 30, right? So for the 3 step, they have used 20. I mean, you can even try that. And if you think that 20 gives a better separation, you can include it as in your report. So that's not you are going to lose marks. So around 4 images would be enough, or 4 or 6, as long as you can read what's inside.
6 in one figure, under one
Yeah,
figure.
under one. Do you know how to do it, right? So you have to put it in sort of a panel, right? And you have to label. You have to label each. Then how do you write the figure legend? So that's figure 1. You have to check the guidelines for Vancouver. That's figure 1. Then you have to write the main title and then describe each subpanel. Like this. Okay, here, now next what we did was the heat map. Yeah, here. So in this method it's a bit difficult to say, right? So maybe you can come up with 3 groups, right? You can see these distinct patterns over here, 3 groups, but then again it's difficult to say. So just mention what hierarchical clustering is and mention the number of groups. Right? Next we come to NMF. Now you have to mention why we are using NMF. That is it. I'll just show you the thoughts in the lecture. After you run NMF, you're going to get these quality scores. Okay? What you want to look at is this co-phonetic score, dispersion and consensus silhouette score. So the consensus silhouette score you get it here, right? So you want to look at the point of maximization, right? So in the co-phonetic score, you see where it drops and where it maximizes after the drop, right? So that's around 5. it comes to dispersion, so here, so it maximizes and then it drops here. Okay. So when it comes to dispersion, it's around 4, right? So when it comes to consensus, you see that's around 4, where it becomes sort of maximum, and then there's a short drop. Okay. So from the scores itself, you can see there's around like 4 to 5.
In the consensus, we have to get the highest.
Yeah,
value.
where it maximizes and there's a sharp drop. Right, so here, and right, so those are the quality scores that we need to check. Next what you got was the consensus maps. So you have you got 4. So for 3, 4, 5 and 6, right? So I have 3 and 4 right now. So how do you check the number of groups here? You check for the definition of the group, right? So more defined it is, the more possible that that is the number of groups that is present, right? So 3, you can clearly see that these two are well defined. So there is a bit of a bit of discoloration here, but you have to compare it with the other groups as well. So when it comes to 4, so these two are well defined, a bit of discoloration here. So 5 and 6, it's even worse, right? So based on the consensus maps, there should be around 3 or 4 groups. Now when it comes to the correlation, how do you get the number of groups? So here, if there were truly well separated three groups, then you would get these red. So these are the meta genes, right? So the meta gene expression, if it is high, you get this red color, and if it is low, it's you get the yellow color, right? So if they were actually well defined, you would get three separate red areas in each row which do not overlap. Okay, but here now you can see that for the first meta gene it does not overlap with any other samples in the other meta genes, right? For the second one, you get this separation over here, and these samples overlap with the third meta gene, right? So they have a high expression in the second one as well as the third one, right? So that is not very defined there. Check for meta gene 4, right? So you can see better separation there, right? So here, you don't get that overlap like in the third. Right. So you can compare them to meta genes 5 and 6 as well. So based on these plots, the survey scores, the consensus maps, and the coefficient maps, we decided on 4 and 5 groups to check by the silhouette plots, right? So next is the silhouette plots. So how do you check the number of whether the number of groups are good or not?
Positive reason.
Yeah, you have to check the
Right.
positive, negative side. So if they are well clustered, so each bar represents a sample. If they are well clustered, they should all be on the positive side. Now this is, and then you have to look at the average silhouette as well. Okay. So that's on 0.39 with 4 groups. Okay, you can see that some are on the negative side, but then you have to compare with the other silhouette plots as well. So for 3, the average silhouette width is 0.38, and you check the silhouette widths for the groups as well. Okay. So here it's around 0.06. We're not looking too good. When it comes to 5, so one group has a negative silhouette width as well. So that's around 0.32. That's the lowest. So based on the silhouette scores, it appears that this is the best. Okay, so that's how you come to the conclusion. After looking at all these plots plus the silhouette plot, you come to the conclusion that there are 4 subgroups. Okay, so finally what we did first, we chose 4 subgroups, and then we assigned each sample the subgroup number. Okay. Okay, so this is the file. So you have each sample and then you have the sum, right? So that is the final output of this workshop. Okay, now any questions? Okay.
Miss, can you tell again how to interpret silhouette? Only the table.
Yeah, you have to look at the number of, you have to look at the clustering, right? So ideally there would be only clusters of the positive side. Now for each subgroup, for each number of subgroups, that is 4, 3, 4, 5, you have subgroups that have negative samples, that have samples on the negatives. Then what you have to do is you have to check these scores, right? So this gives the number of the group, the number of samples that are present in each group, and this is the score, the silhouette score for each group subgroup, right? So you check that, and then you have to check this value at the bottom. Okay, that is point. You have to compare that value amongst the subgroups, and then select the one that has the highest average silhouette. Okay. Okay, any more questions before we move to the next section?
Just could you explain the last part about the mining?
Sorry, yeah. So based on the plots, we decided that there are 4 subgroups, right? So now depending on the results, we just created a file where you take out each sample and assign its relevant subgroup. Okay, so how do we come up with that? That we take from NMM, right? So
What
this
means?
field, so this is an output from NMM, this file, right? So it contains which samples have been assigned which group. So we just take it and we just write it as a separate CSV file. Okay. So this you get. So we didn't run that step because it takes a long time. Okay. But it's here. What we do is, so this is the NMF algorithm. So divide the data set as if there were 4 groups, right? So we tell NMF to divide this build.txt data set as if there were 4 groups and give us the output, which samples are assigned to which group, right? So that file we take it and just convert it to a CSV file, which contains these assignments. Okay. This is what we want in the end. Right, any more questions? Okay, I'll move on to the next. So we assign the colors using this. So if it's group 1, then it's yellow, 2 blue, 3 green, and the last group that is blue, that's blue, that's red. Right? Now we assign those colors and then we plot it. Okay. So what can you tell about the groups? What can you tell about red and blue?
Highly distant technology.
Are there any overlaps? Right, so they seem to be well separated. But when it comes to 3 and 4, there's overlap, right? So you need to look at the 3D plot.
But can we sure of this overlap because we are watching that in the 2D?
Yeah. So that's why you need to take the 3D plot. Okay. So you can see that blue and red are separated. But when it comes to yellow and green, that's quite close together. And you have overlapping regions, right? So what that means is, so there is some biological similarity between the yellow group and the green group, right? So you can do the same for TSNE as well. So TSNE will give you the same result. Okay. So answer these questions in the end. Really helpful. So let's move on to the next one. Now the first thing we did was, for the we looked at the silhouette plot, there are some negatively clustered samples, right? We remove those samples. So these are the steps that we have to remove. You can just mention that. So how many samples will you? There are 30 samples. Those are the negative side. So now when you remove those, you have to remove them from the transcriptomic data set as well. You have to remove them from the transcriptomic data set as well as from the groups object, right? So the groups object is where you store the results. Store the results of the NMF grouping. Right? So where did you get that? It's from NMF over here. It's here, right? So this is the line from NMF. That is where you get the groups object. Now you remove the 30 samples from that object as well. Okay. Now what you are going to do is you are going to perform a t-test. Right? So how are you going to perform the t-test? You can have only 2 groups in the t-test. Okay?
2 samples.
Yeah, 2 samples. Yeah, 2 samples in the t-test. So how you are going to do the comparison is you are going to compare one group versus the others. One group. Now this is for each gene. You are going to compare this for each gene, right? So the mean expression from sample 1 versus the mean expression of all the other groups. Right? have to do a correction because this you run into the multiple hypothesis problem, right? Okay. So what was the correction that we did? That is the Benjamin function. So you have to do this after you get the p-values, right? So where do you do the where do you assign the groups? It's there. Okay, first here you are going to do this for group 1, right? So if you want to do for group 2, 3 and 4, you have to change it here, right? So that 1 becomes 2 if you want to perform experiments. So 2 versus 1, 3, 4, you have to change that number over there. So you adjust the values now. You look at the histogram. Now this plot gives you how much of noise is present in your data set. Okay. So if these bars are all sort of equal, can you take the data set for comparison? That because that means there aren't a lot of genes that are significantly different, right? So you have to get this sort of shape. You have to get low p-values for comparison, right? High number of p-values. Okay. So we need now the next step is we drew a volcano plot. So you need 2 values for that. One is the p-values.
Log
Yeah,
also.
yeah, the adjusted p-value, right? And the fold change. Right? That's the fold change. So you have to look at the significance as well as how much of difference there is present for each gene. Right? So in your script, now if you look at the comments, you can find a difference here, right? So here it's 0.0001. Okay, in the commit, but in the script, in the line, code line, there's 0.001. Okay. So take the value in the code line. Yes. Okay, now this is the volcano plot. This is the fold change and this is the p-value, right? So this is anyways in log. So you converted this to log 10 minus log 10. So the smallest values will appear at the top. Okay. Now here, so why are some in red?
These,
Yeah, because you put the criteria.
they are
Right?
passing both.
Yeah, put the criteria in this code of line. So if the fold change, absolute fold change, that is positive or negative, is greater than 2 and the significance is greater than this value, you highlight it red. Okay. So when you look at the graph, you can see that the genes, DGs which have positive fold change are greater than those in the negative side, right? So that means they are more upregulated genes over here, right? The plot is not symmetrical. So here what we did was we matched, so if you remember from the data set, we have the probe names, right? We just have the probe name, so we have to match the group names to the probe names, right? So we selected the DGs, now we take the probe names of the selected dots represent?
What means?
What do the dots represent? Samples. So these represent the
Groups.
Those represent the groups. And so this represents the expression. Now here this is supposed to be group 1, right? So group 1, this is the top expressing gene. So here you have my expression over here. But for group 2 you get the same high expression for this gene as well. For group 3 you get this like range. So as a mean, if you consider the mean, it's low. There is some separation between the two, but the range overlaps. The upper part of this range overlaps with the group 1 expression, right? So you can say the same for group 4 as well. So can this gene alone separate group 1 from the other groups? No, right? So you can look through multiple genes. You will find there are no minimum number of genes that can separate each subgroup perfectly from the others, right? So you have to select a number of probes to differentiate the subgroup, each subgroup from the others, right? So you can't select just one or two, but you have to select multiple probes. So you have to mention that in your report. Right. Now in the end what did we do? These are the genes that we selected. Okay. We selected all the genes. We selected all the genes that are lower, that have p-value less than this 0.01, and the absolute change is greater than 2. Okay, so those are the inputs for the classifier. Inputs for each subgroup. Okay, finally, you have this part. How do you interpret this?
So how did you get this plot image? Like what is the input you gave? What is the input you gave for this?
So you have this in your files as well. But it's this from line 18, 182 to 195.
Okay, the table that we got after the
Yeah, so now you have to get the genes for each group. Okay?
only specialized gene.
Yeah, so what we are doing here is we take the genes here and we just write it into a text file.
Okay.
For each group, we take the genes and write them onto a text file, so it will look something like this.
Okay.
Okay? Now for each group, you have to do this.
Okay.
So every gene that meets this criteria. Okay? Every gene that meets this criteria is taken into the list. And then we drew the Venn diagram. Okay? So now here you just have to see how many genes are uniquely expressing for each group and what are the most what genes have the most common number of genes. What groups have the most common number of genes, right? So you can see that's most unique genes. What's the group? That's group 2, right? So 137, group 4 has 137, but it has 56 genes overlapping with